Welcome to this lecture. So, this is in the module minimum energy point for low voltage operation and transistor sizing for near threshold circuits, and in this lecture we will be discussing transistor sizing for combinational circuits, a simple back of the envelope calculation method for estimating logical efforts of near threshold voltage circuits. So, we will first discuss the charging and discharging mechanism of near threshold voltage circuits, particularly logic gates which have stacked transistors, and then we will discuss a very simple method to obtain an approximate value of logical effort of these near threshold logic gates, and then we will discuss the logic path sizing, transistor sizing in logic path using this modified logical effort method. So, first we will discuss how do we estimate WP by Wn. Now, what is meant by WP by Wn? Suppose we want to balance the transition times of an inverter. So, you balance them by adjusting the ratio of the widths of N MOSFET and P MOSFET. Lengths are kept at the minimum channel length. So, why do you do this? Because you may sometimes want equal rise and fall transition times, sometimes you may want them to be in a certain ratio, but you do not want the rise and fall transition times to change arbitrarily, because that is not the way you design a logic path. In a logic path, you always have the assumption that the transition times are matching to maximize speed and to minimize short circuit power. To maximize speed and minimize short circuit power, transition times in path must match. This can be seen from several references, especially logical effort. So, for that, all the logic gates in standard cell library must be designed with a certain ratio of the P MOSFET and N MOSFET pulled up and pulled down transistors, so that the transition times are matched. Transition to match rise, fall, transition times, the widths of P MOSFET and N MOSFET must be in a certain ratio. Okay. This is important, but the currents, so the ratio of these P MOSFET and N MOSFET widths in the super threshold voltage regime, that is nominal voltage regime, you may find that you have a certain ratio which fulfills the desired transition time ratio. Suppose the desired transition time ratio, T rise time and fall time ratio is 1, say it may be something else also. It can be 0.7, it can be 0.8, it depends on the size of the transistor cell, that is, it depends on something called track height of the standard cell library and the layout, how if you want smaller gates, less area occupying gates, then you may have some other ratio. It need not be 1 always, but 1 is an example. So, in this to obtain this in the super threshold voltage regime, suppose you have a certain ratio of WP by Wn. Now, in the near threshold voltage regime, the currents are flowing through a different mechanism. In super threshold voltage regime, the currents are flowing mainly because of drift phenomenon, whereas in near threshold or sub threshold voltage regime, the currents are mainly flowing because of diffusion phenomenon. So, the ratio of WP and Wn, which ensures a TR by TF equal to 1, would not remain the same in near threshold voltage regime. Okay. WP by Wn may not be equal to the WP by Wn of near threshold voltage regime. Okay. So, therefore, we need to freshly estimate the WP by Wn for near threshold voltage regime. So, the method that authors in this paper took is that they matched the ion values in near threshold voltage regime. They matched the ion values of the P MOSFET and N MOSFET and said that would give us the ratio of WP and Wn which you want. Okay. So, these are the ion values using simple expressions, though the authors in this paper they refer to an ion value which is different from this. So, but for simplicity we can refer to this, because anyway whatever we estimate is a back of the envelope calculation. It gives us a first estimate. You need to resort to simulations and get to the right values, because a small change in threshold voltage because of say DIBL would lead to a exponential change in the current. So, therefore, whatever you calculate this way is only giving us a first idea. So, this is not a very accurate idea that you can get through these kind of calculations. How do we attempt to get a more accurate way of doing these things, that we will discuss in the next lecture. So, this would give us a first guess for WP by WN. Using this first guess, obtain WP by WN desired using circuit simulations. Now, you would also have a problem that circuit simulations, would they give us the right values, because you may not have, because of variability, especially variability. So, that is a question which we will handle in the next lecture again. So, the characteristic is like this, is not it? So, somewhere here you have threshold voltage. So, this is very well characterized by subthreshold current equation, this by triode or saturation current equation. So, the problem comes about in this regime, which is near threshold. So, the authors in this paper actually use an empirical expression which fits well in this near threshold regime. But the problem with any empirical expression is that you need to first estimate the coefficients for a given PDK, and those coefficients may also be vulnerable to variability, process variability. So, therefore, it is so the approach that we take in the course is that we use these simple expressions and obtain WP by WN, then go for simulations and obtain a better value of WP by WN. Now, we were discussing inverter sizing. Now, let us look at NAND gate sizing. So, NAND gate we have two cases for output discharge. For charging of the output, it is almost like an inverter. Rarely you will find that both the transistors would be charging simultaneously. So, we are not considering that seriously, the simultaneous switching. One of the transistors would be switching. So, if one of the transistors is switching from 1 to 0, the output would get charged, but the charging path is similar as the inverter. Therefore, if we have a reference inverter with the value of WP by WN as discussed previously, then what is the size of, so we want to size the PMOS and NMOS FETs of the NAND gate to have a delay equal to that of the reference inverter for output rise fall cases. Okay. So, now there are 4 cases in this. So, but the output rise is almost similar as that of the inverter. So, that is why you will have this as have a size WP. So, that is not changing. Okay. So, it would have a size which is same as that of the P MOSFET of the inverter. What about N MOSFET? So, now we have a series stack of transistors, and one of the inputs we are considering to be switching. So, one of the inputs will go from 0 to 1 and the other input would already be at VDD, is not? So, there are 2 cases in this. In the first case we are considering that input A is at VDD, input B is switching from 0 to VDD. And in the second case, we would consider that B is at VDD and A is switching from 0 to VDD. So, we will as we will discuss further, the second case would have a larger delay. So, we would size the transistors in such a way that they match the inverter for the second case, because that has a larger delay. That is the approach taken by the authors in this paper. Let us look at the discharge mechanism. So, now transistor B is finding rise in input transition and transistor A is already at VDD. So, at time t is equal to 0, Vx is 0 because A is already at VDD, and so Vgs of transistor B is Vg of transistor B is Vb, and Vgs of transistor B is also Vb because Vx is 0. So, what would happen at time t is equal to 0 when the input starts rising, input of transistor B starts rising. So, it will, the value of IB would rise, is not it? The value of the current IB would increase, and IA is initially 0 at time t is equal to 0, okay. But as soon as IB increases, Vx would also increase because IB increases, and if IA, so it would charge the parasitic capacitance at node X. So, that would increase the value of Vx. So, that would result in a current current IA also, because its gate voltage is at VDD and now drain voltage is also increased a bit. So, that is what we see, that the value of Vx also starts increasing. So, at this point IA will also start assuming some value, and which of them, so IB and IA both have a non-zero value here. So, that is what we observe, and later as you proceed further, Vx starts increasing because IB charges Vx, IA discharges the remaining part of IB. So, therefore, IB is larger, IA is smaller, Cx is getting charged. So, soon the current IA would also start becoming important, and Vout would start falling because of this, and since Vout here is also, let us keep a capacitor CL and Vout here. So, since Vout starts falling and Vx starts rising, you would, Vout starts falling and Vx starts rising, you would find that this transistor would also enter linear regime from saturation. It had begun at saturation, but it would also enter linear regime, and since its output voltage is falling and input is rising, it would have almost a constant current for a while, and then once its input voltage stabilizes to VDD, it would have a falling current, its current would start reducing, okay. So, when its current is constant, even then the output is getting discharged, and what is observed is that the charging of Cx also becomes almost 0. So, Cx is now charged to a certain value and it would remain at that value for a while. So, and then the transistor, the output node is, and at that point what you would find is that IA and IB would almost become equal. IA and IB would almost become equal, and Cx is not charged any further, only Cl is getting discharged, and after a while Cl would get quite discharged, and therefore, IB, the current through current IB would also start falling, and IA would also discharge, IA would become comparable to and slightly larger than IB, and at that time it would, IA would discharge both load capacitance and the parasitic capacitance, and all of them would come to 0 volts. So, that is what you will observe for the lower transistor, upper transistor switching. So, this is the case of upper transistor switching. Now, let us look at the second case of lower transistor switching. So, here this is at VDD already. So, initially transistor B is at VDD. So, Vx would have a value which is Vx of t is equal to 0 is larger than 0, because Vx would start say B is at VDD and A is 0. So, this is a capacitance connected to the output node through transistor B. So, it would get charged till the, so the output, this parasitic capacitance node would Cx would get charged initially, and it would assume a value which reduces the VGS of transistor B to a value which ensures a very small current, almost 0 current through transistor B. So, once it charges to a certain value, it would not the node X would not charge any further, because the VGS of transistor B is such small now that it is not supplying any significant current to charge Cx, and the leakage current of B and A match. So, all this is for time t smaller than 0, Cx charges to value for which IB is nearly 0, or IB leakage is equal to IA leakage. Okay. Now, what happens at time t is equal to t is larger than 0. So, for time t is equal to 0 or larger than or equal to 0. Okay. What would happen? Now, this is rising. Once it rises to a certain value, the input of transistor A, because this is already node X is at a voltage closer to VDD, not exactly VDD. So, it will this node X would start getting discharged, and therefore, IA rises from time t equal to 0. It rises further when the value of input voltage VA is larger than a certain value, because see, the current, exponential current would increase, the near threshold or subthreshold current would increase as an exponential function with respect to input voltage. So, therefore, the increase seems sudden. The switching seems to be sudden. When the input switches, this output, the current switching seems to be sudden. And here you have, therefore, IA would start increasing, and IB would start increasing only when the value of Vx is below a certain value, so that VGS of transistor B has a significant value. Therefore, we find that IA would increase, IB would also increase. Later, as the node V's value reduces significantly, IA would enter such a linear regime, and IB would also enter linear regime, because V out has also fallen somewhat later. So, and then node X is no further charged, not further charged, and the current through current IA and IB would match here. The value at which the current IA and IB match is called, the value for is called Vx target by the authors of this paper, and they assume that the currents of IA and IB would match when Vx reaches Vx target. So, initially what we would observe for lower transistor switching is that initially it is the intermediate node X which is discharged through IA, and later IB also starts assuming an important value, and then it is the output node which is discharged. Because of the exponential nature of the currents, we observe that with increase in gate voltage of VA, there is almost a sudden increase in the current IA, and because Vx also starts falling with that, there is a sudden increase in the current IB. So, it is not as gradual as it is shown here, it is quite sudden, and once node X discharges to a significant value, then the current IB also increases, and you find that node now any further reduction in the value of, and by that time VA has reached VDD. So, by this time you would find that VA has almost reached VDD. So, any reduction in Vx now would result in a reduction in IA. So, that would result in an increase in Vx, because IA is reducing, IB is having a certain value. So, that would result in an increase in Vx. So, let us see this. Initially IA increases, IB is nearly 0, Vx increases. This results in IB increasing, and IB would increase as Vx reduces, and IB would finally match IA. So, Cx no further increases. So, Vx remains almost constant. So, when the input voltage of A reaches near VDD, and by that time if the output V out starts discharging because Vx has reduced, you would find that so after this any further increase, so any further, so if Vx is 2, if Vx falls, since Va is nearly equal to VDD, Ia would fall, but Ia and Ib are nearly equal, so Vx would increase, so that is a feedback. So, you would find that Vx is almost constant once Ib is nearly equal to Ia. So, this value of Vx we are calling Vx target. So, in this paper they call this value of Vx as Vx target or Vx star when Ia is equal to Ib. So, when Ia is equal to Ib, see Ib as Vx starts falling, Ib starts rising, and once Ia becomes equal to Ib, any further reduction in Vx would result in a reduction in Ia. So, then it would result in an indefinite increase in Vx. So, that is not happening. So, once Ia is equal to Ib, Vx remains almost constant because any reduction in Vx would result in a reduction in Ia and charging of Vx by Ib, and therefore, again a rise in Vx. So, there is a feedback here, that is why Vx remains constant, and that value of Vx we call Vx star in this paper, and it is that value. So, Vx remains at Vx star and output discharges as shown here. So, output discharges. So, the effective value of Vx for the output switching is Vx star. So, it is this Vx target, if Vx star, if we find its value, then we would be able to estimate the current Ib which discharges the output node, and that current we match with the reference inverter's discharging current. So, this is the reference inverter. So, we would like to estimate an approximate value of Vx target, Vx star. So, what are we assuming? We are assuming that Vb is already at VDD, Va has reached VDD, Vx is constant during the discharge now at Vx star. Okay. So, if and the currents Ib are matching, Ib and Ia are matching. So, Ib is the discharging current for output node CL, and the output capacitance is equal in the reference inverter and the NAND gate. So, then this is Wp as we had discussed, this would have a value rho Wn. So, we want to estimate that value of rho. So, first we would like to estimate the value of Vx star. So, what is the currents are equal. So, in that case Ib is equal to Ia, it means that in the current equation, since we are also assuming that Vds of A and B for both the transistors is larger than 3 Vt thermal voltage. Therefore, you can neglect the effect of Vds. So, in that case you would have the Vg, the effective gate to source voltage including DIBL, effective overdrive including DIBL and body effect to be equal for both the transistors, that is Vb minus Vx minus lambda Vg lambda Vds. What is the value of Vds? V out minus Vx plus minus gamma, that is body effect, Vbs. So, what is the value of source voltage? It is Vx minus Vth. So, this is proportional to Ib. Similarly, one can obtain for Ia also. So, using this we equate that since Vb is equal to VDD, Va is equal to VDD, Vx is equal to Vx star. So, therefore, you get that for Ib being equal to Ia, you would have VDD minus Vx target plus lambda into V out is getting discharged now. So, it is beginning to discharge. So, it is again at VDD minus Vx star minus lambda Vx VDD, because V out is VDD minus Vx target minus gamma body effect Vx target minus VTA. This is equal to, this is for transistor B. Now, this is equal to a similar overdrive voltage for transistor A. So, what is that? VA is VDD, so VDD minus source voltage is 0 and plus lambda VDS, which is Vx target minus gamma body effect, which is 0 body voltage. So, source voltage is 0 here minus VTA. So, several terms would cancel out. This is for transistor A. So, now you equate both of these and you would obtain Vx star is equal to lambda by 1 plus 2 lambda gamma into VDD. So, now this is a technology related parameter. So, for a given PDK, you would have this would come out to be a constant for a PDK. So, that would mean that you obtain the value of Vx target for a certain width Wn. You arbitrarily choose the value of widths of A and B, keep them equal, obtain the value of Vx target through simulations. So, that will give you the value of this constant gamma lambda by 1 plus 2 lambda plus gamma. This is a constant for a given PDK and you get its value. So, once you get this ratio, you know now this is going to be the same for any size of Wn. Okay. So, then how do you get the value of rho, which makes the discharging current equal that of the reference inverter. So, for that, so you get the value of Vx star. Now, you have obtained the value of Vx star. So, keep for a transistor, keep the source at Vx star, body voltage at Vx star, obtain the value of Ia, okay, obtain the value of the current, and gate voltage as VDD, at VDD obtain the value of the current. Now, this value of current should be equal to the reference inverter's current. For the same CL, if we have an equal CL here, then this current, the current IB should be equal to the reference current here. So, Iref of the inverter for V in equal to VDD and V out equal to VDD. Now, this has a certain width Wn, this has a width Wp. So, what are you be doing? So, get this value of Vx star using the approach that for a given PDK, as we had discussed earlier. For that Vx star, obtain the value of the current through B, through transistor B, by keeping the source voltage and body voltage at Vx star. This current is the discharging current here, and that should match the reference current obtained in this way for Wn. So, for that, for both of them to match, change the size or increase the size of width of transistor B and transistor A simultaneously. Keep width of transistor B and A equal. Now, increase that size and increase. So, when you increase it to a value rho Wn for NAND gate, then you get that IB matches I reference. Okay. That is the approach we have. So, in summary, what are we doing? We are once we found Vx star, we estimate the current through transistor B and let that current equal that of the reference inverter's discharging current Iref, and for that we increase the size of transistor B, increase the width of transistor B to rho Wn, and then so that these currents IB and Iref match. So, that is how we obtain the size of the N MOSFET in this. Now, what is the logical effort of this? Now, this is Wn, Wp, Wp, Wn, rho Wn and rho Wn, and the current carrying charging and discharging capabilities are the same. So, therefore, logical effort is now going to be a ratio of input capacitances. So, the logical effort of this NAND gate is therefore 1 plus, so to be accurate, it is Wp WP plus rho Wn by Wp plus Wn. Now, it depends on the ratio of Wp and Wn. Suppose the ratio of Wp by Wn is 0.8, as the authors in this paper for their PDK they find it to be 0.8. If it is 0.8, so in this paper they find Wp by Wn for reference inverter to be 0.8. So, if it is 0.8, then this would come out to be plus rho divided by 1.8. So, we are assuming that capacitance of a device is proportional to the width of the device. What about parasitic delay? Parasitic delay again with respect to that of the inverter, with respect to the parasitic delay of the inverter. So, the parasitic delay of inverter, so if we assume that this has a parasitic capacitance Cp, this would also have a parasitic capacitance Cp NAND, and if we assume the parasitic capacitance to be proportional to the width, which is not a very bad assumption, because the parasitic capacitances are mainly because of overlap capacitances, gate overlap and spacer and junctions. So, for a regular layout, parasitic capacitance would be almost proportional to the width of the device. So, if we assume that, then the parasitic capacitance at the output node would turn out to be rho plus 2 into 0.8 divided by, so I am sorry. So, this would turn out to be the parasitic capacitance at output node. So, for parasitic capacitance, what they are parasitic delay, what the approach that this paper takes is that parasitic delay of inverter is RC time constant Cp into Rn, RC time constant of the device. Now, what is the value of Rn of NAND? So, this is for inverter. So, what is the Rn of NAND gate? So, since the width of the individual device is increased by R times, so this would be Rn of inverter, let us call it Rni. So, this would be Rni divided by rho, since we have increased the width by rho times. So, what would be the parasitic delay? It would turn out to be, and let we use Elmore delay here, using the parasitic delay would be Cl into 2Rn, because it has to discharge through transistors B and A, plus Cx into Rn. Cx needs to get discharged only through transistor A. So, that is the way they have estimated parasitic delay. Now, we can have a simple, so taking ratio of these two, the parasitic delay of NAND gate and parasitic delay of inverter, if we have some simple estimates of the capacitances, like if we assume that the capacitances are equal to gate, parasitic capacitance is equal to gate capacitance, then we get a simple value for the parasitic delay. So, in this lecture, we discussed a back of the envelope calculation based method for ascertaining Wp by Wn of inverter and for NAND gate as an example of any gate having stacked transistors in near threshold voltage regime. Thank you.